As of today, only one human-made object has left our solar system. Voyager 1, launched in 1977, crossed the heliopause in 2012, entering the interstellar medium. So the question is, how did it do it? And what does this tell us about what would be required for something bigger, like say a spaceship full of people? To answer that question, let's start with the basics. What does it mean to escape the solar system? Our solar system consists of our sun and everything gravitationally bound to it. 8 planets, their moons, asteroids, comets, and Kuiper belt objects. The sun's gravitational pull extends very far, but its influence weakens with distance. The further you get away from the sun, the less effect its gravity has on you. Scientists refer to this as the escape velocity, or the minimum speed an object needs to escape the gravitational pull of a massive body like our sun. For the sun, the escape velocity is roughly 618 kilometers per second, or 4,000 miles per second. Anything traveling faster than that will never fall back down. But here's where things get complicated. To leave the solar system, you have to escape the sun's gravity. That's step 1. But step 2 is much more challenging. You also have to contend with the interstellar medium, or ISM. This is the matter that exists in space between star systems. Thin soup of gas, dust, and radiation that permeates our galaxy. The ISM is not uniform and it's not empty. There are molecular clouds, stellar winds, and remnants of exploded stars that can all impede a spacecraft's journey. To truly escape the solar system, a craft would need to navigate all of these obstacles, including our own heliosphere. Our sun generates a constant stream of charged particles known as the solar wind that creates a bubble-like shield around the solar system called the heliosphere. This shield is not static. It fluctuates and changes shape based on the activity of our sun, but on average, it extends about 120 astronomical units from the sun, where 1 astronomical unit is the distance between the sun and the Earth. To put that in perspective, Voyager 1, the farthest human-made object from Earth, is currently at about 150 astronomical units. That means Voyager 1 is just beyond the edge of our protective bubble. So what does this mean for escaping the solar system? Well, if the heliosphere is our protective bubble, then the edge of that bubble represents the outermost boundary of our current reach. To venture beyond that, we would need to develop technologies that can propel a spacecraft and its crew safely and efficiently through the hazards of interstellar space. Currently, our most powerful rockets rely on chemical reactions to generate thrust. These rockets burn fuel and oxidizer to produce hot, expanding gas that pushes the rocket forward, but chemical rockets are not very energy efficient. They also produce a lot of waste and are limited by the amount of fuel they can carry. One promising alternative is nuclear thermal propulsion, which uses a nuclear reactor to heat a propellant, such as hydrogen, to incredibly high temperatures. The resulting thrust is much more powerful than what chemical rockets can produce. NASA has been developing its nuclear thermal rocket engine for years and plans to test it in the near future. Another option is solar power, which could be harnessed using large mirrors or lenses that focus sunlight onto a spacecraft. As the light bounces off the mirror or passes through the lens, it would create a powerful beam of radiation that accelerates the spacecraft forward. While this technology is still in its infancy, researchers believe it could be used to power spacecraft to high speeds without the need for fuel. These are just 2 examples of the kind of advanced propulsion that would be required to escape the solar system. But regardless of the technology used, the amount of energy required to do so is staggering. According to NASA, it would take at least 100 million metric tons of energy to push a 1,000-ton spacecraft at 10% the speed of light. For comparison, total energy consumption of the United States in 2020 was about 80 million megawatt hours, or about 22 million metric tons of energy. That means it would take almost 5 times the total energy consumption of the SO estates in 1 year to accelerate a 1,000-ton spacecraft to 10% the speed of light. But even with powerful propulsion, the journey through interstellar space would be fraught with danger. The ISM contains high levels of cosmic radiation that can damage human cells and DNA, leading to cancer and other health problems. To protect astronauts on such a journey, we would need to develop new shielding technologies that can absorb and deflect harmful radiation. We might also need to find ways to keep astronauts psychologically and emotionally healthy during such a long voyage. Despite these challenges, many experts believe that with sufficient technological development and international cooperation, it is possible for humans to escape the solar system within the next 100 to 200 years. Some organizations, such as the Future of Life Institute, are already working on plans for interstellar missions. One such plan is Project Starshot, which proposes using a powerful laser to accelerate a nanocraft to a significant fraction of the speed of light. Such a mission could take humans to Alpha Centauri, the closest star system to our own, in just 20 years. In conclusion, the question of whether humans can escape the solar system is a complex one that involves many scientific disciplines. It requires not only advancements in propulsion and shielding technologies, but also innovative solutions to the challenges of interstellar navigation and long-duration spaceflight. However, with continued research and development, as well as international cooperation and a long-term vision, it may become a reality in our lifetime. So the next time you look up at the stars, remember that the vast distances and cosmic hazards that separate us from them may one day be overcome with human ingenuity and determination. What does it mean to escape the solar system? To understand what it means to leave the solar system, we first need to define the system itself. Unlike the neat illustrations in textbooks, the solar system doesn't end at Pluto. Its boundaries are far more complex and much larger than most people imagine. At its core is the Sun, a star that provides over 99.8% of the system's total mass. Its gravity governs everything: the orbits of planets, moons, asteroids, and comets. But its influence doesn't stop at Neptune. It extends outward, thinning with distance, until it eventually blends into the broader gravitational pull of the Milky Way galaxy. Scientists often use several different definitions of the solar system. Planetary boundary, Neptune and the Kuiper belt. For many, the solar system feels like it ends at Neptune, the eighth planet, or perhaps at the icy belt of dwarf planets and comets beyond it. The Kuiper belt, which stretches from about 30 to 50 astronomical unit, from the Sun. 10 is the distance from Earth to the Sun, about 150 million kilometers. Heliosphere boundary. The heliopause, a more physical definition, is the heliopause, the region where the solar wind, a stream of charged particles from the Sun, finally loses its strength against the pressure of interstellar space. This boundary lies between 100 and 120 astronomical units from the Sun. In 2012, Voyager 1 became the first human-made object to cross this boundary, entering true interstellar space, the Oort cloud. The outer shell, but even the heliopause, is not the final word. Surrounding the Sun like a vast spherical shell is the hypothetical Oort cloud, trillions of icy bodies that extend perhaps 100,000. From the Sun, nearly halfway to the next nearest star. If the Oort cloud exists as scientists predict, then the Sun's gravitational reach is unimaginably vast. Escaping the solar system in this sense means overcoming the Sun's grip entirely. So when we ask, can we escape? The answer depends on which boundary we're talking about. Escaping Neptune's orbit is already routine. Escaping the heliosphere has been done by robotic probes. Escaping the Oort cloud, that would mean leaving the Sun's gravitational family forever. A journey of light years. The physics of escape at the heart of this lies a concept from physics: escape velocity. This is the minimum speed an object must have to break free from a body's gravity without further propulsion. For Earth, escape velocity is about 11.2 kilometers per second. For the Sun, it depends on where you start. From Earth's orbit, you'd need a velocity of about 42 kilometers per second to break free of the Sun's gravity entirely. Voyager 1 is moving at about 17 kilometers per second relative to the Sun, fast enough to escape. But it will take tens of thousands of years to leave the Oort cloud. This illustrates a sobering fact. Even our fastest spacecraft move incredibly slowly compared to interstellar scales. The scale of the problem, to put this into perspective: the nearest star system, Alpha Centauri, is about 4.37 light-years away. That's more than 270,000. Voyager 1, traveling at 17 kilometers per second, would need over 70,000 years just to reach that distance. In other words, With our current technology, interstellar travel is far beyond human timescales. Why does this matter? Understanding the solar system's boundaries isn't just a technicality. It sets the stage for the greatest challenge humanity has ever faced: leaving home. Before we talk about futuristic propulsion or generational starships, we must first grasp the enormity of what escape really means. It is not just a matter of rockets or engineering. It is a confrontation with scale, with the vastness of space itself. And so, our journey begins here, at the edge of understanding. With the first spacecraft already reaching beyond the sun's protective bubble, our solar system is like the surface of a calm lake, mirroring the life of our blue planet. The sun, large and luminous, presides over this domain. 8 major planets, each with its own story, revolve around it. The inner rocky planets, Mercury, Venus, Earth, and Mars, are terrestrial worlds, solid and dense. Beyond them lies the asteroid belt, a rocky-strewn field marking the transition to the outer gas giants. Jupiter, Saturn, Neptune, and Uranus, composed mainly of gases and liquids. Pluto, once considered the 9th planet, reigns over a distant realm of icy bodies called the Kuiper Belt, comets and other icy visitors from the distant. Oort cloud occasionally disrupt this stately dance, yet there's more to the solar system than meets the eye. Interstellar space, the sun's outermost envelope, marks the beginning of interstellar space. Within this region, the solar wind, a constant stream of charged particles from the sun, pushes outward. It forms a protective bubble known as the heliopause, shielding us from harmful cosmic radiation. However, beyond this bubble, there is little that can shield us from the truly mind-boggling distances involved in space travel. Let us embark on a journey that starts at Earth and goes beyond the familiar confines of the planetary system. We begin our voyage at the orbit of Mars, about 150 million miles or 225 million kilometers from the Sun. As we leave the inner planets behind, we enter the asteroid belt. While it may seem empty, this region is teeming with millions of asteroids ranging in size from Vesta, the largest at 329 miles or 530 kilometers across, to countless others only a few feet wide. After traversing the asteroid belt, we arrive at the orbit of Jupiter. It's the largest gas giant and the 5th planet from the Sun. Its colossal presence dominates this region, with a diameter over 86,000 miles or 140 kilometers across. Leaving Jupiter behind, we journey to the orbit of Neptune, the 8th and farthest known planet in the solar system. With a diameter of 30,599 miles, or 49,244 kilometers, Neptune is an ice giant. Finally, we come to the hypothetical boundary of the solar system, the Oort cloud, thought to be a sphere of icy bodies extending up to 100,000 astronomical units. From the Sun, our journey continues into the great unknown, venturing into interstellar space. Here we encounter the heliopause, the outer edge of the Sun's influence, where the solar wind meets the interstellar medium. Crossing this threshold, we are greeted by the breathtaking vista of our galactic neighborhood. Looking back, we see the faint glow of the Milky Way, a band of light stretching across the darkness of space. Between the stars, wisps of clouds, remnants of supernova, mark the birthplaces of new stars. The tapestry of space is filled with wonders, each more awe-inspiring than the last. Yet, despite these marvels, we remain aware of the immensity of the cosmic ocean that surrounds us. For while the boundaries of our solar system may seem distant, they are merely a gateway to the boundless expanse of the universe. Now let's meet the intrepid explorers that have ventured beyond the confines of our planetary system. These pioneering spacecraft have pushed the boundaries of our knowledge and brought us closer to understanding our place in the cosmos. Let's start with Voyager 1, the interstellar scout launched in 1977. Its mission to explore Jupiter and Saturn led it beyond the orbit of Neptune. In 2012, it crossed the heliopause, becoming the first human-made object to reach interstellar space. Voyager 1 carries a plaque with images and sounds of Earth to convey our story to any civilizations it might encounter. Next, we turn to Voyager 2, twin sibling to Voyager 1, though not as fortunate to witness the birth of a new star. Voyager 2 did capture the remarkable view of the churning atmosphere of Neptune during its flyby in 1989. These missions marked significant Milestones in our exploration of the outer reaches of the solar system. Pioneer 10 and 11, the trailblazers that followed the Mariner 9 orbiter to explore Jupiter and Saturn. They were the first to cross the asteroid belt and send back the first close-up images of the outer planets. Pioneer 10 even carried a plaque with a universal symbol of peace depicting a mother and child intended to communicate our peaceful intentions to extraterrestrial life. And finally, we have New Horizons. The Pluto probe launched in 2006. After a 9-year journey, it reached Pluto in 2015, providing the first close-up views of the dwarf planet and its moons. Continuing its mission, New Horizons has explored other Kuiper Belt objects like Arrokoth, deepening our understanding of the formation of our solar system. Each of these missions has played a crucial role in expanding our knowledge of the solar system and the universe beyond. They serve as a testament to human curiosity and our relentless pursuit of understanding the cosmos. And as we reflect on their achievements, we are inspired to push the boundaries of exploration even further. So let's get into the meat of this episode. This is probably one of my favorite parts because it's all about the future. Yes, so far we've been talking about the past, about the history of our journey to the stars. But now it's time to turn our eyes forward and ask ourselves, how will we really get out there? How can we cross the seemingly impassable gulf of interstellar space? Is it possible? Let's start with the obvious. Today, the fastest spacecraft traveling through our solar system is not Voyager 1 or New Horizons. It's a tiny probe named Parker's Solar Probe. Launched in 2018, it has already achieved speeds of over 300,000 miles per hour, about 133 kilometers per second. That's fast. So fast that it literally touches the sun. But even that speed isn't nearly enough. Using the same physics that governs the solar system, NASA has calculated that Parker's Solar Probe would need to travel for 66,000 years to reach the nearest star system. Even if we could build a spaceship that can go faster than light, which according to Einstein's theory is impossible, if we did break the cosmic speed limit, it would still take at least 40,000 years to get to Alpha Centauri. In terms of interstellar distances, we are essentially stuck. Our best hope lies in finding a way to bend the rules of physics. Of course, there's always warp drives, wormholes, and hyperspace, things that belong in science fiction movies. But in real life, our best bet is something called generational ships. The idea is deceptively simple. Build a massive spacecraft that contains everything a crew of several 1,000 people would need to survive a generation or more, including plenty of food, water, air, and most importantly, the means to sustain themselves and produce more generations until they arrive at their destination. Sounds great in theory, right? Well, there are some major hurdles. For example, you would need to keep everyone on board healthy. That means taking into account things like psychology, sociology, biology, pharmacology, and medicine. A lot of people might think that having children on such a ship would be the best solution. However, the issue with that is that it comes with a host of unique medical issues, especially in space. Additionally, since the ship's course cannot change over decades, centuries, or millennia, no one on board could decide to leave. No one could return home. And finally, how would you launch something that big? According to physicist and science communicator Dr. Becky Smethurst, such a vessel would require a tremendous amount of energy, many millions of times greater than that released by the biggest supernova. If we wanted to build a starship capable of reaching Alpha Centauri within 100,000 years, then we'd have to build it bigger than Earth. Dr. Schmidt concludes that this kind of starship is beyond our technological capabilities and possibly beyond our physical limits. But maybe we don't have to go that far. Many researchers believe that interstellar travel could be possible with new propulsion technologies. Nuclear fusion rockets, antimatter engines, and solar sails are just a few of the ideas that are being considered. Some of these concepts are closer to reality than others. For example, NASA's project, which is developing a solar electric propulsion system that uses powerful lasers to propel a spacecraft at up to 10%. The speed of light has received renewed attention. If you want to hear more about these propulsion systems, check out our previous episode on faster-than-light travel. But even with new technology, the numbers remain daunting. Traveling at 10% the speed of light, it would still take 80,000 years to reach Alpha Centauri. So it seems that interstellar travel is not impossible. It's just extremely difficult. But there is hope. In 2016, a group of engineers proposed an audacious plan. Use nanotechnology to create a self-assembling spacecraft that could travel at up to 20% the speed of light. While still in its infancy, this technology could one day make interstellar travel a reality. The idea is to create a swarm of tiny spacecraft that would work together to form a larger ship capable of traveling through interstellar space. The advantage of this approach is that each individual spacecraft would be relatively small, making it easier to launch multiple copies from Earth. Once in space, the spacecraft would use a combination of laser propulsion and solar sails to accelerate to high speeds. As they travel, they would use their onboard computers to communicate with each other and coordinate their movements. When they reach their destination, the spacecraft would disassemble themselves into smaller probes that would land on the planet's surface and search for signs of life. Now, here's the million-dollar question. How big does a spaceship have to be to have a chance of surviving the journey through interstellar space? Unfortunately, there is no easy answer to this question. It depends on a number of factors, including the size of the crew, the amount of supplies needed to sustain them, and the type of propulsion system used. However, some rough estimates suggest that a starship would need to be at least 1 kilometer long and contain at least 1 million tons of mass to have a chance of surviving the journey. This is obviously a huge undertaking, but it's not impossible. With advances in technology, we may one day be able to build spaceships that are large enough to support human life for long periods of time. But here's the thing. We may not need to build a giant starship to reach the nearest stars. Interstellar space is full of resources that could be used to support human life, such as water, minerals, and even fuel. In fact, some scientists believe that asteroids and comets could be used as bases for refueling and resupplying spacecraft on their way to other star systems. This could potentially reduce the amount of resources needed to be carried on board a starship, making it smaller and easier to build. But perhaps the most exciting possibility is the use of artificial gravity. Several scientists have proposed the idea of using rotating space stations or rings to create artificial gravity. This could potentially eliminate the need for a starship to carry supplies for long periods of time, as well as reducing the health risks to the crew. If we could develop a way to create artificial gravity, it could potentially revolutionize interstellar travel and make it possible for humans to reach the nearest stars within a reasonable time frame. So is interstellar travel possible? The answer is yes. It's just really hard. But human beings have always been up for a challenge, and we've overcome seemingly impossible odds before. Who knows what the future may hold? Yes. Maybe one day we will be able to travel to the stars. That brings us to the end of this episode. In the last 2 segments, we discussed the historic first attempts to venture beyond our solar system and the monumental challenges of interstellar travel. Now it's time to shift our focus to the latest discoveries and advancements that are shaping the future of space exploration. There's a lot happening out there, and we want to bring you the most up-to-date information. Our solar system has been put on notice. It's only a matter of time before something catastrophic strikes Earth. What then? Are we doomed? No. Humanity has a plan. A top-secret plan created by the richest and most influential people on Earth. We call it the Exodus Plan. You might think it's crazy, but hear me out. There's logic to their madness. In this video, we go in to explore the Exodus Plan and how humanity will escape the solar system. When the proverbial flies hit the proverbial fan. Humanity's robotic probes have made it into interstellar space, but they are crawling compared to the scale of the galaxy. If we're serious about escaping the solar system within a human lifetime, or even within a few centuries, we face a staggering list of problems. These challenges are not science fiction daydreams. They're the cutting edge of physics, engineering, and cosmology. Each represents an unsolved frontier. 1. The propulsion problem. The biggest obstacle is speed. Our fastest spacecraft, like Voyager 1, travels at around 17 kilometers per second. To reach Alpha Centauri in a human lifetime, say 100 years, a ship would need to travel at about 10% the speed of light. That's 30,000 kilometers per second, nearly 2,000 times faster than Voyager. How could we possibly achieve this? Several proposed propulsion methods exist. Nuclear fusion drives fusion. The process that powers stars could release enormous energy. Concepts like the Daedalus Project, 1970s. Imagined a spacecraft powered by fusion pellets, ignited by lasers. If built, it could theoretically reach about 10% of light speed, but controlled fusion remains an unsolved challenge even here on Earth. Antimatter engines, when matter meets antimatter, they annihilate, releasing pure energy. In theory, an antimatter drive could be the most efficient engine imaginable. The problem? It can barely produce a few nanograms of antimatter in labs at astronomical cost. As light sails, instead of carrying fuel, we could push spacecraft with giant sails using powerful lasers from Earth or orbit. This is the idea behind Breakthrough Starshot, a real initiative funded by private investors. If successful, it could send tiny probes to Alpha Centauri within a few decades. The challenge is building lasers powerful enough and sails durable enough to survive the journey. Warp drives and exotic physics. Some physicists have speculated about bending space-time itself. Inspired by Einstein's relativity, the Alcubierre drive, for example, proposes contracting space in front of a ship and expanding it behind. While mathematically interesting, it requires exotic negative energy that may not exist in usable form. At present, none of these solutions are ready, but they represent humanity's imagination stretched to the limits of known physics. 2. The radiation barrier. Interstellar space is not empty. It is filled with high-energy cosmic rays and charged particles that could destroy electronics and harm living organisms. Our current spacecraft endured this because they are robotic and shielded. But for human passengers, decades exposed to such radiation would be fatal. Potential solutions include heavy shielding, which makes spacecraft too massive, magnetic or plasma shields, mimicking Earth's magnetic field, or more radically modifying biology itself through genetic engineering or cybernetics. Now let's return to the video. With all these issues in mind, it's hard to believe that humanity would ever mount an interstellar escape. Yet hope is not lost. Elon Musk, the eccentric billionaire who founded Tesla and SpaceX, has a radical plan. He wants to build a self-sustaining city on Mars and use it as a backup plan for humanity in case Earth gets destroyed. Others are less enthusiastic about Mars, arguing that it's too similar to Earth and too hostile to life. They dream of distant stars like Proxima Centauri, which has a small rocky planet in its habitable zone. More ambitiously, physicist Michio Kaku believes humanity will eventually spread across the galaxy, becoming a multiplanetary species. But why rush? Kaku thinks we should start exploring other star systems as soon as possible, even without the capability to reach them. This is the purpose of the Breakthrough Starshot initiative, which plans to send tiny probes to Alpha Centauri within decades. These probes will not carry life to new worlds, but they could search for signs of life. And they may one day pave the way for real interstellar explorers. So don't panic. If Earth gets destroyed, humanity has a plan. We will flee to Mars or find another planet. Or maybe we'll find a way to survive the destruction of our solar system. Who knows? What matters is that we keep trying to escape certain doom. Can we escape the solar system? As children, we dream of faraway adventures on distant planets. We tell stories of intrepid explorers charting unknown worlds and discovering new life forms among the cosmos. It seems as though such fantasies are confined to our childhood imaginations. After all, when we grow up, we learn that the solar system is our home, the Earth our shelter, and the Sun our protector. Traveling to other star systems seems like an impossible task. Yet recent advancements in technology and discoveries have shifted our perspective once again. Scientists are now boldly venturing where only imagination used to tread. If you're curious to know whether we can escape the solar system, stick around for an enlightening ride. 1. Earth will not last forever for now. Earth is our sanctuary. Yes. But it will not remain so indefinitely. In 1 billion years, the sun's increasing brightness will make Earth too hot for liquid water. In 5 billion years, the sun will expand into a red giant, engulfing Mercury and Venus, and possibly Earth itself. Even before those distant catastrophes, there are nearer-term threats. Asteroid impacts, supervolcanoes, nuclear war, climate collapse. While these may not destroy all life, they could reset human civilization dramatically. If we want humanity to survive across cosmic time, remaining on a single planet, or even a single solar system is risky. 2. Planetary limits. and the search for a new Earth, our solar system gives us no easy second home. Mars is a candidate for colonization, but it is dry, cold, and has no magnetic field. Terraforming it would take centuries or longer. Europa and Enceladus may harbor subsurface oceans, but they are ice-covered moons, not Earth-like surfaces. Titan has a thick atmosphere, but it's minus 180 degrees Celsius, with seas of methane instead of water. None of these are true second Earths. If we want another planet as hospitable as our own, we must look to exoplanets around other stars. Already, telescopes like Kepler and TESS have identified thousands of candidate worlds, some in the habitable zone, where liquid water could exist. The dream of a new Earth is not fantasy, it's a scientific target, but those worlds are light years away. And so, interstellar travel becomes not just an adventure, but a survival strategy. 3. The civilizational imperative. Carl Sagan once said, "All civilizations become either spacefaring or extinct." Why? Because civilizations that remain confined to one fragile world are at the mercy of cosmic accidents and their own destructive tendencies. By spreading out, humanity creates resilience. A multi-planet or multi-star civilization cannot be destroyed by a single asteroid, war, or collapse. This is not only about survival, it is about flourishing. Escaping the solar system would allow humanity to expand its resources, its creativity, and its diversity across the galaxy. 4. Technological spin-offs and near-term benefits. Even if interstellar travel remains centuries away, the pursuit of it has immediate benefits. Research into fusion power for propulsion could revolutionize energy here on Earth. Advances in life support systems could help with sustainability and recycling technology at home. Developing long-duration space habitats could teach us how to live more efficiently with finite resources. In other words, the road to the stars may also solve problems here on Earth. 5. Psychological and cultural dimensions. There is also a psychological need. Humans are explorers by nature. For tens of thousands of years, we have pushed into new frontiers, across continents, across oceans, into the skies, and then into space. To stop to say this far and no further would be to deny something fundamental about who we are. The effort to escape the solar system may define not just our survival, but our identity. Future historians may look back and ask, were we the civilization that looked up and reached out? Or were we the civilization that turned inward until we disappeared? 6. Ethical questions. Of course, there are ethical dilemmas. Should we attempt to colonize other worlds if they already host microbial or intelligent life? Should resources be devoted to space exploration while billions still struggle on Earth? Could spreading humanity across the stars also spread our conflicts, inequalities, and mistakes? These are not simple questions, but avoiding them will not stop the march of time. The universe will not wait for us. The human connection. So can we escape the solar system? The practical answer may still be not yet. But the human answer is clear. We must at least try. Because interstellar escape is not just about distance, propulsion, or physics. It is about ensuring that the story of humanity does not end prematurely. It is about becoming more than a local species of one small planet. It is about survival, but also about meaning. The journey is already underway. The spacecraft we have launched are the first threads of a much larger tapestry. They are silent now, but they point toward a future where we may follow. The dawn of discovery, the quest to understand the vast expanse of the universe and our place within it, is a journey as old as humanity itself. In the beginning, we gazed at the celestial tapestry and wove myths and legends around the patterns we saw. As time marched on, our understanding evolved from mythology to astrology, from astrology to astronomy, and finally to the modern science of astrophysics. Today, we stand at the threshold of a new understanding. We are on the cusp of unraveling the deepest mysteries of the cosmos. Our journey begins with Galileo Galilei, the Italian astronomer who turned the telescope towards the heavens and revealed a universe that was not static, but dynamic. Not perfect, but flawed. With his groundbreaking discoveries, he laid the foundation for modern astronomy and showed us that the Earth is not the center of the universe. Fast forward to the 19th century, and we find ourselves in the midst of a scientific revolution. Scientists like Nicolaus Copernicus, Johannes Kepler, and Isaac Newton had redefined our understanding of the cosmos. Copernicus proposed a heliocentric model of the solar system with the sun at the center. Kepler discovered that planets move in elliptical orbits. Newton developed his law of universal gravitation, all laying the groundwork for a new view of our place in the universe. In the 20th century, the pace of discovery accelerated dramatically. With the launch of Sputnik, the first artificial satellite to orbit the Earth in 1957, the space age began, and with it, a new era in our understanding of the universe. Over the decades that followed, we sent astronauts to the Moon, explored the surface of Mars, and ventured deep into the farthest reaches of our solar system. With each new mission, we brought back more data, more images, and more evidence of the incredible complexity and beauty of the universe. Today, we stand at the forefront of this journey of discovery with an unprecedented understanding of the universe and our place within it. We know that our solar system is just one of countless star systems in the Milky Way, and that the Milky Way is just one galaxy among billions in the observable universe. We have discovered thousands of exoplanets, some of which may be habitable, and we are searching for signs of life beyond Earth. Our telescopes peer deep into the cosmos, allowing us to see back through time and witness the birth of stars and galaxies. We are mapping the large-scale structure of the universe, identifying the patterns and features that make it so hauntingly beautiful. But perhaps the most exciting development in our quest for understanding has been the discovery of the expanding universe. This discovery, made in the early 20th century, revolutionized our understanding of the cosmos and earned the Nobel Prize for Physics in 1933. Edwin Hubble, an American astronomer, made this groundbreaking discovery while studying distant galaxies. He noticed that these galaxies were all moving away from us, and that the farther away a galaxy was, the faster it was receding. This observation led him to conclude that the universe was expanding, a conclusion that changed our understanding of the cosmos forever. The discovery of the expanding universe has had a profound impact on our understanding of the nature and evolution of the cosmos. It provided the key piece of evidence for the Big Bang theory, the prevailing cosmological model for the universe. According to this theory, the universe began as an extremely hot and dense singularity, and has been expanding and cooling ever since. Hubble's discovery also raised many new questions. What caused the universe to expand in the first place? Is the expansion accelerating? And what is the ultimate fate of the universe? These questions have driven generations of astronomers and cosmologists to push the boundaries of our understanding. With the advent of powerful new telescopes and space missions, we are closer than ever to answering these profound questions. The James Webb Space Telescope, for instance, is providing an unprecedented view of the early universe, allowing us to peer back some 13.5 billion years to witness the formation of the first galaxies. Other missions, such as the European Space Agency, Euclid, and the Dark Energy Survey, are mapping the large-scale structure of the universe to better understand the distribution of galaxies and the role of dark energy in the acceleration of the universe. As we continue to explore the vast expanse of the cosmos, we are uncovering secrets that were previously unimaginable. The discovery of the expanding universe was a pivotal moment in our quest to understand the cosmos. It opened up new frontiers of exploration and inspired generations of scientists to push the boundaries of human knowledge. As we continue to probe the depths of space, we can be sure that the discoveries that await us will be as awe-inspiring and transformative as the discovery of the expanding universe itself. The dream of interstellar escape did not emerge suddenly. It is the product of centuries of science, observation, and invention. Every telescope aimed at the sky, every spacecraft launched, every theory of physics tested. All of it has built the foundation for humanity's greatest question: can we leave the solar system? The answer? A resounding yes. The pieces of the puzzle have been in place for centuries. Now we are assembling them. More than 4 billion kilometers away, orbiting the Sun in a path similar to Earth's, lies the first piece of the puzzle, Mars. Unlike Earth, Mars lacks a global magnetic field, meaning its atmosphere is slowly being stripped away by the solar wind. This makes Mars an inhospitable frozen desert today, but with its abundance of water, ice, and carbon dioxide, it may be possible to warm up Mars with enough energy to make it habitable again, an idea that has gained steam in recent years. According to research, Terraforming Mars will require warming the planet by several degrees and increasing atmospheric pressure by 10 times. Although challenging, current technology and resources are enough to start the process. Several proposals are already underway. Off the top of my head, Elon Musk plans to use solar mirrors or laser beams to warm Mars and maintain it at a livable temperature. But whether we choose to colonize Mars or find an alien world to call home, both options require fuel. And that is where the second piece of the puzzle comes in. We need nuclear fusion. Currently, the main method of generating electricity is through nuclear fission, which is highly efficient but unsustainable because of the limited supply of uranium. Fusion, however, is different. Instead of fission, nuclear fusion involves forcing lighter atomic nuclei together to form heavier ones. This is the same process that powers our sun, and scientists believe that a sustained fusion reaction can produce roughly 10 times more energy than fission. There are multiple approaches to achieve this, including the inertial confinement approach used by the National Ignition Facility at the Lawrence Livermore National Laboratory in California, which recently achieved ignition, meaning the team produced a net gain of 1.5 for the first time. While significant, this is still far from the amount of fuel needed for an actual spaceship. Other methods, such as magnetic confinement, use powerful magnets to confine plasma in donut-shaped devices called tokamaks. The largest tokamak in the world is the Joint European Torus, or JET, located in the United Kingdom. In December 2021, JET achieved its highest ever fusion performance, producing a fusion reaction equivalent to 59 megawatts of power, lasting for 5 times longer than the previous record of 1.6 seconds. These experiments hold the key to developing the third piece of the puzzle, the propulsion system. Nuclear thermal and electric propulsion have been proposed for crewed missions to Mars and beyond. However, they require huge amounts of propellant, making takeoffs difficult. Nuclear fusion offers an alternative solution. Research suggests that a fusion-powered spaceship would produce thrust about 6 times greater than chemical rockets. Such thrust would allow the spacecraft to carry more cargo and travel faster, potentially shaving months off the journey to Mars. And when we finally leave the solar system, we must navigate in deep space. To understand navigation in deep space, we need to understand our fourth piece of the puzzle, the solar system's edge. Our solar system extends beyond Neptune, Pluto, and the Kuiper Belt to the outermost boundary of the heliosphere. The heliosphere is a bubble-like region of space created by the sun's constant stream of charged particles known as the solar wind. As the solar wind expands, it collides with the gas and dust of the surrounding interstellar medium, creating a shock wave that forms the heliopause. Interstellar probes like Voyager 1 and 2 have explored this region, providing the first direct evidence of the heliopause and a better understanding of our solar system. S-Edge. Voyager 1 crossed the heliopause in 2012, and its measurements revealed a heliospheric, its boundary with a thickness of 180 million kilometers. Voyager. To confirm these findings, crossing the heliopause in 2018, and providing further insights into this previously unexplored region of space. These missions have revealed valuable information about our place in the galaxy, enabling us to study phenomena such as the interstellar wind, cosmic rays, and the behavior of our solar system's outermost boundary. At this stage, we are well equipped to chart a course outside the solar system. But we need a destination, which brings us to the fifth piece of the puzzle. We need exoplanets. Exoplanets lie outside our solar system, and some are potentially habitable. Astronomers use various methods to discover these distant worlds, including the transit method, which involves observing the dimming of starlight as a planet passes in front of its host star. With advancements in technology, scientists have identified numerous exoplanets and continue to refine the search for those that could support life. One promising candidate is Proxima Centauri b, a rocky planet orbiting the nearest star to our Sun. Discovered in 2016, it is located in the habitable zone of its star and is thought to be one of the best targets in the hunt for extraterrestrial life. While no current technology can directly image the planet, scientists are hopeful that future instruments may provide insights into its composition and potential habitability. Currently, the most advanced and powerful space telescope is the James Webb Space Telescope. It is capable of detecting the faint infrared light from distant galaxies and exoplanets, helping scientists analyze the atmospheres of exoplanets to search for signs of life. It can see farther back in time than any other telescope, allowing researchers to observe some of the first galaxies that formed after the Big Bang. Additionally, the James Webb is equipped with a suite of 4 instruments that enable it to detect infrared light from planets and other systems, measure their mass, and study their atmospheres. This capability is expected to revolutionize the search for habitable worlds and provide insights into the formation and evolution of planetary systems. With all these pieces in place, we can launch the 6th piece of the puzzle, the spacecraft. The concept of a spacecraft capable of interstellar travel dates back to the early 20th century with the works of scientists such as Konstantin Tsiolkovsky, who theorized the use of multi-stage rockets to achieve high speeds. The 1950s and 60s saw the development of spacecraft like the Voyager, which were designed to explore the outer reaches of our solar system. More recently, projects such as SpaceX's Starship and Blue Origin's orbital class have proposed vehicles capable of carrying large payloads and cruise beyond Earth's orbit. These spacecraft are expected to play a crucial role in our ability to leave the solar system. Starship, for instance, is a reusable 2-stage super heavy lift launch vehicle designed by SpaceX. It is intended to be the most powerful rocket ever built, capable of lifting over 100 tons into orbit and eventually venturing into interstellar space. Meanwhile, Blue Origin's orbital class is an even more ambitious project aiming to transport up to 40 tons to low Earth orbit. This would make it one of the most powerful launch systems in history. These vehicles represent the cutting edge of space exploration and promise to open up new possibilities for interstellar travel. Finally, the 7th piece of the puzzle is time, the unknown variable. Leaving the solar system is a monumental task requiring the coming together of physics, technology, and exploration. It is a testament to the power of human curiosity and our desire to understand the universe around us. Whether we are talking about the theoretical concepts of nuclear fusion or the practical applications of spacecraft design, each piece of the puzzle contributes to our understanding of the complex challenges involved in leaving our planetary cradle. As we continue to push the boundaries of scientific knowledge and technological innovation, we may find that the time to leave the solar system is closer than we think. However, this is only the beginning of our story. There are many more challenges ahead before we can leave the solar system. First, we must deal with orbital mechanics. Launching a spacecraft out of the solar system requires precise timing and trajectory calculations. Scientists must consider the gravitational pull of other planets and the spacecraft's fuel efficiency to determine the optimal path. Second, there is the issue of propulsion systems. Currently, chemical rockets are the primary means of launching spacecraft, but they are not powerful enough to escape the solar system. We need new propulsion systems like nuclear fusion to achieve the necessary speeds. Third, communication becomes a challenge over vast distances. As the spacecraft travels farther away, the signal sent from Earth becomes weaker and takes longer to reach the craft. This poses a significant obstacle in terms of monitoring and controlling the mission. Fourth, there are the ethical considerations of interstellar exploration. If we decide to colonize an exoplanet, we must consider the potential impact on any native life forms and the ethical implications of altering distant ecosystems. Fifth, there is the risk of contamination. If we send a spacecraft to an exoplanet without taking proper precautions, we could contaminate it with Earth-based microbes, potentially disrupting any existing life. Sixth, we must not forget the human element. Sending a crew on an interstellar mission requires careful planning to ensure their health and safety. We need to develop new technologies to keep the crew safe during the long journey and ensure their well-being once they reach their destination. Seventh, there is the cost factor. All these challenges require substantial financial investment, and we must consider the economic implications of committing resources to interstellar exploration. Finally, there is the unknown. We have never sent a spacecraft beyond the solar system, so there are many unknowns that we must be prepared to encounter. We could discover new phenomena or challenges that we have not even considered. Despite all these challenges, the dream of leaving the solar system continues to captivate us. As we continue to explore the universe, we may find that the time to leave our planetary cradle is closer than we think. And when we do, we will be ready. We have traced the boundaries of the solar system, celebrated the spacecraft already leaving it, explored the frontiers of propulsion, and considered why escaping matters for humanity's survival. But the real question remains, Where does this lead? Where will we go, and who will we become? To answer these questions, let's think bigger than any single mission or even any one person. Let's look at the incredible journey ahead for humanity across the galaxy and through the millennia. The future of interstellar travel will not arrive all at once. It will unfold in stages, some within our lifetimes, others across centuries, and still others that reach beyond imagination. First, let's talk about the next century, specifically the next 30 years. This is the nearest part of the timeline, because it's the one that we can predict the best. Within the next 3 decades, we will not see humans traveling to other stars. No crewed spaceships will cross interstellar distances. That distinction will belong to robots. Breakthrough Starshot will hopefully take its first tiny steps toward reality. Its plan calls for fleets of Gram-sized spacecraft reaching up to half the speed of light and propelled by Earth-based lasers. If all goes well, this could happen in just over a decade. With around 1,000 spacecraft launched every year, we might actually see a small fleet of them arrive at Alpha Centauri in just 20 to 30 years. It would circle the star system for 2 years imaging planets and collecting data about their environment. The data would take 40 years to transmit back to Earth, meaning we wouldn't receive the first images until well into the second half of this century. Still, that means the first true images of another star system captured by machines sent by humanity will be within a single human lifetime. NASA and ESA are also exploring advanced concepts for nuclear propulsion, missions that could travel much faster than chemical rockets, and give us a detailed look at the outer solar system's boundary regions. Voyager is nearly 50 years old, yet still sending home valuable science from the edge of our cosmic backyard. A new generation of nuclear-powered explorers will bring a fresh perspective on the region where the solar system begins to meet interstellar space. These robotic scouts will be our eyes and ears, the first true pathfinders into interstellar space. They will prepare the way for the next stage of expansion, which will occur over the next few centuries. But before we leap to other stars, humanity must master our own solar system. And that process has already begun. The next few hundred years will see permanent settlements on the Moon and Mars, mining of asteroids and habitats orbiting in free space. These will be our proving grounds, the testing grounds, for long-duration spaceflight. Rotating O'Neill cylinders could sustain thousands, even millions of people in comfortable environments free of gravity's effects. They will serve as a crucial training ground, allowing us to learn how to live in space for long periods. Some will venture farther. There are hundreds of thousands of comets and icy Kuiper Belt objects that could be mined for water, volatiles, and even minerals. Capturing one of these chunks of the early solar system could provide scientists with invaluable insights into the conditions that shape the worlds around our sun. Others will study the outer reaches of our planetary system, searching for signs of what lies beyond. By the time the 24th century rolls around, humanity should have mastered living and working in space. Only then will we be ready for the leap beyond. It won't be easy. Traveling between stars takes time, especially at the speeds we can manage today. Our closest neighboring star systems are 4 light-years away, and the next closest ones are almost 5. That means it would take years to get there, and the same amount of time for a reply to travel back. This doesn't bode well for rapid-fire conversation, so what are we to do while we wait? Perhaps we can find entertainment in our surroundings, as this illustration suggests, with plenty of room to roam and explore. Generations might pass before we can establish meaningful contact with other star systems. Even at near-light speeds, it would take centuries to traverse the vast distances between us. So to reach those distant stars, humanity will need to embrace the millennial scale of interstellar travel. By the middle of the next millennium, humanity will face some difficult decisions. If fusion power becomes practical, we might construct generation ships, massive vessels designed to carry communities across the stars. These ships would be ecosystems in motion, sustaining multiple generations of people on their way to a new home. For example, the ship's designers might try to recreate natural systems, growing plants and raising animals to ensure passengers have access to fresh food during their multi-century voyage. Generation ships would likely travel at a small fraction of light speed, limited by the power available to drive them. At such speeds, these ships would take centuries or millennia to reach their destinations, meaning each vessel would need to be fully self-sufficient. Passengers would live, work, procreate, and die aboard the ship. Their descendants would be born into deep space and never know anything else. By the time they arrived at their destination, the original passengers would be long dead and gone. These journeys would be less like expeditions and more like the founding of entirely new civilizations in transit. A single ship might contain tens of thousands of people, meaning there would be plenty of opportunity for new societies to form. The passengers would face many challenges during their travels and possibly even encounter alien civilizations along the way. But if all goes well, these journeys would allow humanity to finally escape the bounds of the solar system. If we are lucky, we will see several of these ships launch during this period, opening up multiple pathways to the stars. But there will be risks involved in this process. Every generation ship would be a closed system, vulnerable to the effects of radiation, micrometeor impacts, and mechanical failures. If anything should befall a ship, its passengers would have no hope of rescue, stranded in the cold vacuum of space. In fact, we might lose contact with multiple ships over the course of the millennium. But if a few succeed, then humanity will truly spread its wings and begin to fly among the stars. And here's where things start to get speculative. The far future is full of possibilities, but none are guaranteed to come true. By the far future, humanity may have achieved technologies that today seem impossible. Fusion and antimatter drives might push ships to 10 to 20% of light speed. Beamed propulsion might allow starships to accelerate without carrying heavy fuel. If exotic physics allows, though it is highly speculative, warp drives or wormholes might one day make interstellar travel faster than relativity permits. At this scale, the entire galaxy could open up. A civilization millions of years old could spread to thousands of stars, perhaps even reshape the galaxy itself. We might discover other civilizations along the way, some advanced, some primitive. We could help guide these civilizations along their paths to enlightenment or inadvertently destroy them. Or we could leave them alone, studying from afar, hoping they will one day reach the stars themselves. As we venture farther into the universe, we enter the longest view, the one that stretches beyond galaxies. To survive cosmic time, an intelligent species would need to continually migrate, seeking new energy sources and perhaps even harnessing black holes or the decay of matter itself. If the heat death of the universe is our goal, we will have truly escaped the solar system. This brings us back to the beginning and the final questions. Will humanity actually do this? The technology is hard, the timescale is immense, but history shows that what once seemed impossible, flight, space travel, splitting the atom, eventually became reality. Should we do this? Is our destiny to spread across the stars, or should we focus on preserving the single world we already have? Perhaps both are necessary. What will we become? By the time we reach other stars, we may no longer be recognizably human. We might be hybrids of biology and machine, digital minds traveling at light speed, or entirely new forms of life descended from us. Escaping the solar system is not just about leaving a place. It is about evolving into something larger. Let's close with a simple thought experiment. Imagine looking up at the night sky 10,000 years from now. What will you see? We know the planets will still be there, but the stars will be different.
Ow.
They will twinkle in unfamiliar patterns, and several will be missing. The constellations you know will no longer exist. In that alien sky, you will be a stranger. You will realize that your story is a tiny thread woven into the fabric of the universe. But the more you look, the more you will understand that your story is not unique. Everywhere you look, there are signs of other stories. The stories of stars and planets giving birth to life and launching civilizations to the stars. You will know then that the universe is vast and full of wonder, but also full of echoes of our own story. You will understand that we are all part of something much larger than ourselves, and that the future of space belongs to everyone. Thank you for watching. Keep looking up.